this chapter. Okay, so last time we finished up the last chapter there. It's going to be on our exam, which is, in case you're not sure, 1 week from today. Yes, this is what they say. So this then would be should be exam 3 stuff from this point on here. So in this chapter and a little bit of some other chapters, a little mixture of some things. We're going to talk about chemical equations, balancing equations, and we'll also talk about chemical reactions, ways to classify reactions, different types of reactions. So let's just start with that chemical equation. So in a process where obviously we have one or more substances that create new substances, that's a chemical reaction. Remember, a chemical reaction is a chemical change. So what we start with and what we end with are fundamentally different things. You cannot get back the original substances by any type of physical means. You can't freeze it, boil it, do whatever else you want to do to it and get it back. The way we represent chemical reactions are with chemical equations, and there's some important parts of our chemical equations. We always have reactants on the left-hand side of the arrow, and our reactants are our starting material, and it goes to our products, which are on the right-hand side of the arrow. We do see a lot of other things in an equation. We do see the states oftentimes given next to the substances in the equation. So it could be in the solid state, the liquid state, the gas state, or the aqueous state, which is a water environment, and it's really a solution. We might have talked about this before, but just in case we didn't, there is, again, a difference between liquid and something that has the aqueous sort of designation. They are both really in the liquid state, but they are different things. Something that is a liquid is usually a pure substance. So just one thing by itself, like water, for example, would get the designation of a liquid. Now, something aqueous is usually made by dissolving something in another part of a solution. So aqueous is typically a solution that has two parts. It has the solute, which is the smaller part of a solution, and it has the solvent, which is the larger part of a solution. And typically speaking, for example, if we took water, which is a pure liquid, and we put some solid sodium chloride in there, the solid sodium chloride or salt would dissolve in the water, and we would be left with a sodium chloride solution that gets the aqueous symbol. So a solution is a homogeneous mixture, and a homogeneous mixture means it's the same throughout, so everything will dissolve into it. So there is, again, a distinction between those things, between liquid and aqueous. So liquid is usually one thing by itself. Aqueous is usually a couple of things mixed together in a mixture where everything mixes really well together. Some other things that we do see as well in an equation, and that has to do sometimes with the arrow. Sometimes we may see a delta symbol, which in this case would mean heat. Sometimes we may see water written on top of the arrow, which would indicate that something's being dissolved in water. Although a lot of times we do use chemical equations for chemical changes and chemical reactions, we can use a chemical equation for a physical change, like, for example, H2O going from liquid to H2O that's going to solid. That's basically the formation of ice. And although that's a physical change, we can use an equation to represent that. And clearly, in this case, the states of each of these guys would be really important, so you understand what is happening, rather than just having water on both sides. Most commonly as well, what we see on top of the arrow a lot of times is a catalyst. And a catalyst is not a reactant. It's not a product, and it does not get used up in the reaction. Really, a catalyst is there in most cases to speed up the reaction. And a way a catalyst is able to speed up a reaction is it basically finds a more alternative way for that reaction to take place, a more efficient way if you want to think about it. And what it does is it actually lowers the energy of the reactants so they can get to the other side quicker, more guys can get to the other side. So very common on top of the arrow, we'll see things like sometimes catalysts are metals like platinum. Sometimes catalysts are also solutions like H plus is sometimes written, which means it's an acidic catalyst. So these are very common things that we see in chemical equations, all these different sort of symbols. Any questions on any of those there? Now, when we do look at a chemical equation, there's different ways that we could kind of look at it and read it. So for example, if we have this equation here, which is our magnesium burning and oxygen, maybe you did this before in a previous class. This is the one usually they have you burn the magnesium and go observe what happens, but don't look directly at it because it's very bright and it'll blind you and stuff like that. That's my favorite instructions. Observe what happens, but don't look at it and stuff like that. But it's bright enough you could actually see it without looking directly at it. But when we look at it, we can look at these coefficients, for example, in the balanced equation, and we could say that in this case, 2 atoms of magnesium react with 1 molecule of O2. It makes 2 formula units of magnesium oxide. This is a term that's sometimes used for ionic compounds because they are not held together by sharing of electrons. So sometimes people use the word formula unit instead of like a compound or something like that, or a molecule because it's technically not sharing electrons when it's ionic. Also, you'll also sometimes see how we calculated the molar mass for things that are ionic. Sometimes people will call it the formula mass for the same reason. It's technically not sharing electrons. So if you come across that, that's what that represents. The relationship that we'll use the most when we get into stoichiometry is what is referred to as the mole to mole relationship. And that also comes from the balanced equation, the coefficients. We could say 2 moles of magnesium react with 1 mole of O2 to give us 2 moles of magnesium oxide. The last part here is the conservation of mass. And since we have a conservation of the elements in a chemical reaction, if we start with 1 magnesium on the left and 1 on the right, they both have the same mass of like 24 or so grams. And same thing with the oxygens. We have the same oxygen on the left and right, which is about 32 grams. So we should start and end with the same amount of grams of each of those things. Those coefficients do not represent the grams of each of those things is the one thing they do not represent. We have the conservation of our elements because the only thing that happens in a chemical reaction is we pretty much break all the bonds on the reactant side, like we talked about with our bonding type of situation, and we remake them on our product side. And since bonds are all about electrons, electrons are not in the nucleus, right? What particle is really important for the element so it doesn't change? Protons, electrons, neutrons, which one tells you what the element is? It is protons, yeah. So in a chemical reaction, since we are only playing with bonds, which are electrons, we don't touch anything in the nucleus. So that's again why we have to balance equations, as we'll talk about, and we should start and end with the same number of elements on each side. They may just be in different compounds when we're all said and done. So let's talk about balancing equations and talk about some of the steps here. So for example, the first thing that you want to do is, especially if you're given something in words, you want to make sure you get the correct formulas down first and then do the balancing part of it. So very often people will kind of do that together. They'll try to balance and write the formulas. And usually what happens is people will end up with the wrong formulas. They'll be there all day trying to balance something that will never balance. It happens when you're given everything in words. And most commonly happens a lot of times when you're like given the reactants and you need to predict what's on the product side. People always want to kind of balance and write the formulas at the same time. So the order that you should always do it is, forget about the balancing part. You should make sure that you are starting with the basic correct formulas for everything before you begin. And just like you would do in the naming chapter and all that, put it together correctly, get all the right formulas, and then you should balance. So to balance equations, there's many different approaches. I personally am a fan of starting with what looks easy and balancing those things. I usually like to save elements that are in a lot of places, so a lot of different sort of compounds for the end. Some people say tackle the more difficult one first and save the easier ones for the end, but it is sort of personal preference. So if we were going to take this one right here, which is what we got there, C2H6. So we have this equation here, C2H6 plus O2, a little CO2 plus some water. When we balance these equations, a couple of things are really important. The only thing that we could change is the coefficients that are in front. So we should never change the subscripts when we're balancing an equation, because if I change the subscripts, I just change what that thing is, right? So we can't change the subscripts. We also can't do any weird things that people sometimes like to do as well, which is like insert a number in between things. So for example, you can't go like C2O2. I'm just going to put a 2 there in front of in the middle of everybody. So you can't do those things. You can't change the subscripts, only the coefficients that come in front of the number. You obviously need to continue until you pretty much have the same number of elements on both sides. And when you're all done balancing the equation, there's basically two things you have to make sure of. All the coefficients need to be whole numbers. And they also need to be the simplest set of whole numbers. So what I mean by that is if you balance an equation like this, 2a plus 4b goes to 6c, we'll just say that this is balanced. Although it is balanced, I could do what with all those coefficients? I could divide them all by 2, yeah? And you should, to get the properly balanced equation, which in this example would be something like this. So this sometimes happens because people could see larger numbers to balance it, and it can be balanced. But if you can still go through and reduce down all of your coefficients by a common number and still have whole numbers, that gives you the properly balanced equation, not the one where you haven't reduced it down. All right, so let's take a look at this equation here. So the deal is, I personally like to make like a little table here. It helps organize things in a lot of cases. Reactant side, product side. I'll actually do it the other way. Let's do it that way. Reactant side, product side, we'll list our elements: carbon, hydrogen, and oxygen in this case. And the benefits of a table sometimes is it can sort of help guide you where to start, maybe where to go next, keep track of everything. So on the left-hand side here, we got 2 carbons. Right-hand side, we got 1. Left-hand side, we have 6 hydrogens, which is right there. Right-hand side there, we have 2. Left-hand side, we got 2 oxygens. And on the right-hand side, we have 2 oxygens there, plus 1 more there, which makes 3. So in this particular case, I'm going to start with personally what seems to be the easiest. One of the easiest things here would be carbon. It's only in one thing on each side, so I could fix the carbon by putting a coefficient in front of the CO2. That coefficient does go to everybody behind it, and that's going to give me 2 carbons. That will still have 2 hydrogens. I now have 4 oxygens in the first one, plus 1 more in the second one, which makes a 5 in this case. Yeah. Now, I fixed the carbon, but I'm still have some trouble on some other ones here. I'm going to go with next hydrogen. And the reason I'm choosing hydrogen in this case is oxygen's in a couple places here and by itself. So that's kind of a mess. Hydrogen is only in one place on each side. So that makes it a little bit easier to balance. So that is what I'm going to attack first here. So I got 6 hydrogens on the left. I need 6 on the right. So I'm going to lay me up a 3 there in front of the hydrogen on the right. That once again does go to everybody behind it as well. And that gives me 2 carbons, 6 hydrogens. And now in terms of my oxygen, I still have 4 on the first one. And now I have 3 times 1, which is 3. And that now gets me to 7. Any questions so far? All right, so clearly I've balanced everything but the oxygens. I clearly do not want to touch anything on the right-hand side because I'm already locked in, if you will. So really, I got to go to the left-hand side here. I'll get that left and right done here. I have to go left-hand side here to fix it. And I really need a 7 in this case, but I have a 2. So in this particular case, we can fix it by actually using a fraction to fix it. And I could take something like 7/2 will do that for me. And when I do that, that will give me 2 carbons. That will give me 6 hydrogens. And when I take 7/2 times 2, that gives me 7, which would give me 7 oxygens in this case. That is balanced, yes. Is that correctly balanced, by the way? It is not correctly balanced because I have a fraction. So this is a good illustration. You could use a fraction to balance the equation, but you do have to get rid of it. So you can't leave it as a fraction. So to get rid of it, we're going to multiply everything by, I think they call that the denominator still, multiply everything by the bottom guy there. And that's going to give me 2 of the C2H6 plus 7O2 gives me 4 CO2 plus 6 waters. And if I didn't screw anything up here, we should still be balanced. So let's see, we got 2 times 2 is 4 carbons on the left. We got 4 on the right. We have 2 times 6, which is 12 hydrogens on the left. 6 times 2 is 12 on the right. 7 times 2 is 14 oxygens. And I got 8 oxygens in the first guy and 6 in the second guy there. That looks like 14 to me as well. So you definitely can use a fraction to balance it, but you do have to clear it. It oftentimes happens like this, where you got like one element and multiple things on one side, and kind of like the diatomic form of the element on the other by itself. That's commonly when it happens. How do you choose the right fraction? It's a pretty simple recipe. If you remember, we needed a 7. So the top number is always the number you need. Bottom number should always match that number. And then you'll always have the right fraction. So that's a really easy way to do that. Question on that balancing equation there. As you probably know, you should always make sure that your equation is balanced. So if you're given an equation and there's numbers, you should take a second and take a look at it. It probably is balanced, but just make sure. If you're given an equation where there's no numbers, you should definitely take a hard look at it and make sure that it is balanced, or if not, make sure that you do balance it. Any question on those steps there? All right, then let's do some here. Okay, let's take a look. So once again here, we got on the left, 1 nitrogen, 2 nitrogens on the right, 1 oxygen on the left, 1 on the right, 2 hydrogens on the left, and 2 on the right. So everything's balanced here except for nitrogen, so clearly a good place to start. We'll put a 2 there to balance it. That gives us 2 nitrogen. Oxygen, once again, that also goes to the oxygen, so that would be 2 and 2 here. So that what most often happens is you do fix something else, and kind of screw up something else. So the next easiest thing here looks like that perhaps it should be oxygens where we want to go to balance next. And we need to put a 2 on the right-hand side. Once again, that is going to go to everybody behind. So that's going to give me 2 nitrogens. That will give me 2 oxygens. And that will then give me 4 hydrogens. At this point, we could hopefully see we just need to come back over here to the left and put a 2 to give us 4, 2, and 2 are balanced. Yes. Any questions on that one there? All right, a few more examples here. Balance up this one. Okay, let's take a look. So making our table here, we got 3 carbons on the left, 1 on the right, 8 hydrogens on the left, and 2 on the right. 2 oxygens on the left there. Remember, we do have oxygen here, which is 2, plus 1 more there, which is 3 in this case. So again, here I'm going to start with what seems pretty easy. We got 1 carbon on each side, so I'm going to fix the carbon first. I'm going to go 3 here. That's going to give me 3 carbons. We will still have 2 hydrogens, and once again, that 3 will go to everybody behind it. So that's 6 there, plus 1 more. Gets me 7 oxygens at this point. Next is going to be hydrogen. Again, for the same reasoning, we got oxygen in a lot of places, so I'm just going to kind of save that for the end. At this point, to fix the hydrogen, we're going to go with a 4 right about there, and that will get distributed to everybody behind. That gives me 3 carbons. We now have 8 hydrogens. We still got the 6 oxygens there, and we just added 4 more to it, which gives us 10 oxygens at this point. Now we could hopefully see, we just need to go to the right there to fix the oxygen, and that's going to require a 5 in this case, giving us 3, 8, and 5 times 2, which is 10. Any questions on that one there? All right, a few more here. So balance this one up here. This is diboron trioxide reacts with water to form boric acid. So let's take a look at it then. So if we add up here, we have 2 borons and 1. Oxygen, we have 3 there, and 1 more is 4. And as I was just mentioning, this 3 does get multiplied into the parentheses. So we do have 3 oxygens there in the parentheses. And then we also have 3 hydrogens as well, and 2 on that side. So not a lot to work with here, except for the boron seems like a good place to start. So we're going to put a 2 there. This 2 does go to here, and it also goes to whatever's in the parentheses as well. So that would give us 2 borons. Once again, we basically have 3 times 1 times 2, which is 6 oxygens, and same thing with the hydrogen, 3 times 1, and then multiply on the outside there, gets us to 6. Right? So essentially what that is, right, is you have to start with 3 of them, and then you just put a 2, so you just double them, right? So you got 6 and 6 basically going on there at that point. At that point, we can't do anything now with what's on the right, so we should go to the left. Once again, here I'm going to tackle the hydrogen as, again, oxygen's in multiple places there on the left-hand side. So I'm going to lay me up a 3 right about there. That's going to give me still 2 borons. That's going to give me now this guy getting distributed. So I got 3 oxygens there and another 3 here, which is 6. And I have 3 times 2, which is 6 hydrogen. So in this case, by fixing the hydrogen, which sometimes happens, everything else sort of fell into place in terms of the oxygen. And now we are balanced. Any questions on that there? All right. And try this one here. So, again, here we got 1 nitrogen and 1, so that's good. We got 3 hydrogens and 2, and 2 oxygens and an oxygen. Each of these guys there makes 2. So everything's balanced except for the hydrogen. So sometimes you do have to put some coefficients on both sides to start. So in this case, the common number for hydrogen is 6. To get my hydrogen to 6 on this side, I need a 2. And to get this guy to 6 there, I need a 3. That's going to give me 2 nitrogens. Multiplying that 2 to the 3 gives me 6 hydrogens and 2 oxygens. Still have 1 nitrogen on this side. 3 times 2 is 6 hydrogens. We have 1 oxygen there and 3 there, which does give us 4 in this case. So we fixed the hydrogen, but pretty much screwed up everything else. Again, here I'm going to go to nitrogen next, which seems the easiest. I could just put a 2 there. That's going to give me 2 nitrogens. We still have 6 hydrogens. Oxygen, we're now down to 2 there and 3 there, which is 5. Now, by saving my oxygen for the last there, I could clearly see I could just go to my O2 there, and perhaps this is a good fraction situation. Again, on top is the number we need, which is 5. On the bottom should match that number, which is 2. And now we should be in business. That's going to be a 2, a 6, and that will give me 5. Again, here we do need to clear it, so we cannot leave it as a fraction. So we're going to multiply everybody by 2 here, and that will give us 4 of the NH3 plus 5O2 gives me 4NO plus 6H2O. And again, if I did not screw up here, we should still be balanced. We got 4 nitrogens. It's 50-50 chance. There's 4 nitrogens over there as well. We got 12 hydrogens. 6 times 2 on the right is 12. Oxygens, 5 times 2 is 10. We got 4 oxygens there and 6 there, which is 10 in this case. Yeah. Any questions on that? So again, another case where we kind of see the element in its diatomic form by itself, and in a couple of things on the right hand side, very common sort of place where fractions pop up. Any question on balancing there? So clearly you need to be able to balance equations, should always make sure that they are balanced. Before we finish up talking about balancing here really quick, now we've been doing it with the table and sort of element by element, but when you do have equations that have polyatomic ions in it, like these guys here, there's PO4 on both sides, a little carbonate action on both sides. A lot of times it's easier to just balance them as units rather than element by element, so you don't have a lot of multiplying in and multiplying out. So if I were to tackle this one, I would start with the phosphate here because I basically have the same number of carbonates on each side. So on the left-hand side, I basically have 2 phosphates. Right-hand side, I have 1. So I'm going to put a 2 here to give me my 2 phosphates. When you do this method of balancing by these polyatomic ions, once you put the coefficient in front to take care of the polyatomic ion, that is where you should go next, the other guy that's there. So that is now going to change my sodium to 6. So I'm going to go to the left-hand side and make my sodium a 6 over there. That just got my sodium to a 6, but now changed my carbonate to a 3. So that's where you should go next. And I'm going to put a 3 for my carbonate, which then gives me a 3 for my iron. And now I am done. I am balanced. So it's much quicker when you have these polyatomic ions on each side that look the same to kind of keep them as whole units and balance them as whole units. You can go element by element, but there's a lot more chance probably for a mistake and multiplying in and multiplying out. Any questions on that one there? So if we take the same approach here on the bottom, we got sulfate and sulfate. We got hydroxide and hydroxide. So again, in this case, you could start with either one, and maybe one would work better than the other. So for example, let's say I started with the sulfate here. I got 3 sulfates on the right, 1 on the left. So I'm going to put a 3 here. That's going to give me 6 silvers. So that's where I'm going to go next. I'm going to put a 6 there in front of my silver. That gives me 6 silvers and now 6 hydroxides, which is where I want to go next. And I'm going to put a 2 there. And now I am balanced at that point. Now, let's just say that maybe you chose wrong, right? So maybe, you chose the other guy to start with. Let's just say we started with the hydroxide and you went with a 3 first. And now you have 3 silvers and you come over here and go, that's not going to work, right? Obviously, in this case. So you could basically adjust your thing by going, well, the common number between 3 and 2 is 6. So maybe I need a 3 there and make this a 6. And now you could basically kind of pick up and finish it that way as well. So even if you kind of chose wrong, you could sort of adjust midway if you needed to, or just erase them and start with the other one and you'll be fine as well. Question on balancing equations. Okay, so let's then talk about chemical reactions now, some different types of chemical reactions. But before we do, we're going to talk about electrolytes. And electrolytes are substances that when they go for a swim, they basically break apart into ions. And when they do break apart into ions, they're able to conduct electricity really well. because of the presence of those ions, the positive cations and negative anions. They help complete the circuit and conduct electricity really, really well. Non-electrolytes are substances that will dissolve, but will not produce any ions. So they will not produce any ions, so no ions. And because of the lack of ions, they do not conduct electricity really well. As you can see here, that is a light bulb with some electrodes in a non-electrolyte. Light bulb's off, does not conduct electricity. There are different types of electrolytes. There's a weak electrolyte, which produces a few ions. So even though it doesn't produce a lot of ions, there are still some ions floating around in that solution and enough for it to conduct electricity. And if you looked at the light bulb, basically it'll come on, but it'll be kind of dim. And there's strong electrolytes, which 100% break apart and produce a lot of ions in solution, tons of ions in solution. And because there's a lot of ions in solution in a strong electrolyte, it will conduct electricity really, really well. The light bulb will go off very, very brightly. So for example, water is a good or bad conductor of electricity, pure water. Pure water is actually a bad conductor of electricity. It's covalent, right? There is no ions in it. Just so we're clear, the water that comes out of your faucet is not pure water. You will electrocute yourself if you decide to blow dry your hair in the shower. Yes, so do not do that. Good advice always. They actually put ions into the water to clean it. And so there's a lot of ions in there, which is why you will get electrocuted. But pure water, if you have nothing but H2O, actually has no ions and it's a bad conductor of electricity. So let's take a look at these a little closer. So a strong electrolyte is something that will 100% break apart in solution. So if we take something like a sodium chloride solution, which is NaCl, it is going to 100% break apart into our sodium ion and chloride ions. And basically in that solution, you have a ton of these guys floating around. And again, it's going to completely dissociate into ions and conduct electricity really, really well. Pretty much most ionic compounds are strong electrolytes. They will break apart in solution 100%. You have absolutely none of these units still together in that solution. So there's no sodium chloride unit still together. Basically, you have ions floating around, really ions surrounded by waters in that solution, which is how it dissolves. A weak electrolyte, on the other hand, is something that will break apart a little bit, but a weak electrolyte will mainly stay together. So a lot of weak acids are weak electrolytes. A lot of strong acids are strong electrolytes as well. So when we talk about kind of strong acids, there's kind of a core four that, are pretty strong. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and nitric acid. These are pretty much strong acids. By the way, strong bases are also strong electrolytes as well, like sodium hydroxide, potassium hydroxide. Pretty much on the periodic table there, if you go like, sodium, potassium, hang a left or right over there to calcium, strontium, put group 1 or group 2 with some hydroxide, probably have a strong base on your hand. And those guys would 100% break apart in a solution. So if you had a hydrochloric acid solution, in that solution, you would have H plus ions floating around and chloride ions floating around. 100% of it would be those ions, which is why, again, you would not have any of those guys in the solution. And that's why it's really a strong acid, because it's able to produce a lot of free H plus really, really quickly. Same thing if we take sodium hydroxide, which is a popular strong base, and you put that into solution, you basically have sodium ions floating around and a bunch of hydroxide ions. And you have none of these guys still together. And because it's able to produce a lot of hydroxide really quickly, that's why it's considered a strong base. So any strong acid or strong base, any ionic compound are typically strong electrolytes. When they're in solution, they're not staying together. They're going to break apart into ions. And that's where we find ions pretty much floating around the solution. That's where positive guys and negative guys hang out. They like to just float around in the solution, basically part or liquid part of it. Now, weak electrolyte, something like this, which is acetic acid. You'll be very familiar with it after the titration experiment. That's basically vinegar, or the main component there of vinegar, which is acetic acid. It's a weak acid, and it will break apart into acetate and the H+ ion. You'll get a few of these guys in solution, but you will mainly stay together. And usually a weak electrolyte, we see arrows heading in both directions, and that implies that it's a reversible reaction. It has a forward direction, going from reactants to products. And at some point, those products will head back the other way in what is referred to as the reverse direction. It will eventually reach what is known as chemical equilibrium, or 200B, pretty much the subject of 200B. And basically what that means is the rate of the forward direction will equal the rate of the reverse direction. So just as quickly as it goes one way, it's going to come back the other way just as quickly. A strong electrolyte, as you can see here, has a one-way arrow. Everybody's dumping out to the product side. Nobody's coming back the other way. There's not going to set up an equilibrium. It's just all going to break apart. In a weak electrolyte, it will go back and forth. Hydrofluoric acid is also another weak acid and a weak electrolyte. When it breaks apart into H+ and F-. So in solution, if you have HF, you have a lot of HFs still together in that solution. And you got a little bit of some free H+ and free F- floating around in there. So that's why it's still able to conduct electricity, because there's still a few ions floating around. That's why in the light bulb example is dim rather than super bright. In the light bulb example, the strong electrolyte would be super bright because there's a lot of ions in that solution. It's also why it's still considered an acid, because although it doesn't produce anywhere near what hydrochloric acid would produce, it's still able to produce some H+ that's free in the solution. So it's still considered an acid because of that. It's able to release some of that H+. Any questions on that there? Yeah. Uh-huh. So what was happening, and a quick explanation, I think, of your question is this. When you did it all and you dissolved your solid into with your acid and all that, what actually happens, what we're going to talk about later in this chapter, which was like a redox reaction, and electrons were lost. And what happens is when you have something, say like, what do we use there? Silver, right? Or like silver metal, right? Has no charge, no oxidation state when you do it. So when you treat this, it goes through a redox reaction. And what happens is the silver actually loses electrons. And when it loses electrons, it's now going to become positively charged. And it's at that point that it starts to swim around in the liquid part with your acid and actually gets surrounded by a bunch of waters and stuff like that. There's other ions in there. We had nitrate, I think, thrown around there because we did nitric acid, also floating around, also surrounded by waters. It is those guys that are surrounded by water in that sort of liquid part, which keeps them apart from each other, which is why they're no longer a solid, right? And they're floating around. What happens when you then heated it, right, is you got rid of basically all the waters that were surrounding these guys, right? They evaporated off. And at that point, what was left, I guess the better one would be we had chloride floating around in there as well. What was left at that point in there is basically your silver ion, your chloride ion, no water to get in the way. That's a super strong electrostatic attraction, and that's why they come back together, and you have the solid that was left over in your evaporating dish. Was that your question? All right. So here we've been talking about electrolytes, which is actually really important for a certain type of reaction that we'll talk about. But as was mentioned, we have our strong electrolytes, which will 100%, as we've been talking about, break apart into ions. Virtually, there's pretty much none of the whole unit still together in that solution. Everybody's went for a swim and swimming around by themselves, floating. In a weak electrolyte, on the other hand, as I mentioned, you pretty much have everybody staying together, but you do have some generation of guys that will fall apart a little bit, and you'll get some ions in that solution. So since it's still able to produce some ions, it's still considered an electrolyte, and it's a weak electrolyte, still able to conduct electricity for that reason as well, because it has produced a few ions. So there's our acetic acid. As I mentioned, that reversible reaction, and weak electrolytes typically have those arrows heading in both directions. And most weak acids, most weak bases, by the way, in terms of weak acids, any of those ones not on that list that we kind of listed earlier that were strong acids is probably a weak acid. Probably one of the most common weak bases you come across, I would say, is ammonia actually is a weak base. And you may be looking at ammonia and going, it doesn't have hydroxide in it. But what happens with ammonia is it is able to actually react with water and act as a base, which means it actually will accept an H plus from water. And when it does so, it will produce NH4 plus ammonium, and it will produce hydroxide. And that is why ammonia is a weak base, because it's able to produce hydroxide in solution. But it is a weak base. So unlike sodium hydroxide, which once it goes for a swim will completely break apart, produce a lot of OH minus in that solution, ammonia's got to do a little bit of work there to produce hydroxide. You're not going to produce as much of it. So when we have weak electrolytes, we sort of think of them as staying together. And when we have strong electrolytes, we think of them in a sort of reaction as coming apart and making those ions. And sort of tying into, I think, what we were talking about there at the very end, this is really how things dissolve. So when you have an ionic compound, which is a strong electrolyte, something like sodium chloride, when it goes for a swim, it will make sodium ions and chloride ions, but they do get surrounded by water, and that's essentially how it dissolves. And again, it is the oxygen side of water, which is more negative, which is attracted to the positive ion, while actually the positive side of water, which is the hydrogen, is attracted to the negative ion. And that is what basically allows a solid ionic compound like sodium chloride to dissolve. You help it along because we usually stir, right? Adds energy, throws a ton of water all over all those ions, and helps the dissolving process, helps them pluck them off. It is a super strong attraction force between sodium and chloride, the sodium ion and chloride ion, but there's just so much water involved that they're able to pluck them off away from each other and surround them. And it is what really keeps those guys from coming back together. It is also sort of the shorthand we use when we write aqueous next to something. It implies that those guys are basically surrounded by water as they're floating around those ions in that particular solution. And again, as we talked about, what happens when we start to heat it is there goes all those waters. Now these ions can return back together and we re-see the solid basically form, very much like we did in those couple of experiments where we evaporated off at the end all that water, and then we were left with the solid residue in the evaporating dishes at the end. A non-electrolyte, as I mentioned before, is something that can dissolve. So sugar is a good example of that. If we take sugar, it will dissolve, but it will not produce any ions, because sugar is basically carbon, hydrogen, and oxygen held together by electrons and bonding, covalent bonding, so it doesn't produce any ions. By the way, when somebody dissolves like this, right, when we do dissolve something like sodium chloride in water, that's a physical or chemical change. That is a physical change, yeah, because we could still get the water back, right? And we could get the salt back by evaporating it off, right? If we really wanted the water, we could collect all the steam, cool it back down, you get the water, and you have your salt back. So a solution, which is a homogeneous mixture, is actually a physical change. There's really nothing reacting. We just can't see it anymore because there's a lot of water around everybody, and it basically makes it so we can't see it. So sometimes people think when we dissolve something, it's actually a chemical reaction happening, and it's not. It's really a physical change that is occurring. So with our sugar here, we will get it to dissolve, but again, it will not produce any ions. So here are some examples of strong electrolytes. So here's some of our strong acids, strong bases, and ionic compounds. Pretty much if you have any of those, you could consider them in solution 100% breaking apart. Now, if you have your weak electrolytes, that's acetic acid, hydrofluoric acid, nitrous acid, ammonia, are all weak electrolytes. They will mainly stay together but produce a few ions. And here, these are some examples of non-electrolytes. They will dissolve but no ions. So basically, no ions, few ions, lots of ions. In that case, yeah. All right, any question on electrolytes there? All right, so how do we know if we mix a couple things together, whether or not we will get a solid to form? And what we look at is what is referred to as solubility. And solubility is the maximum amount of solute that will dissolve in a given amount of solvent. So a solution, which again, as we talked about, I think earlier today, which usually you will get that aqueous symbol, is again made up of two parts, and that is the solute, which is the smaller part, and that is the solvent, which is the larger part. So in our example, when we take sodium chloride and we take water, water is our solvent, sodium chloride is our solute, and when we put them together, we get a sodium chloride solution that basically has sodium ions floating around and chloride ions basically floating around in it. There is a maximum amount of solutes that you could get to dissolve, or solid that you could get to dissolve, and it is based on temperature. So typically, if you're trying to dissolve something that's a solid in a liquid, usually the higher the temperature, the more solid you could get to dissolve in it. And that's again because there's more energy as you do that, right? You increase the temperature, it gets more energy, allows more ions to kind of get away from each other. Opposite is true. You lower the temperature, usually you can get less amount of solute to dissolve in there. And there is a maximum amount that will dissolve, as you might have ever done. If you take sugar, right, you could get some packets of sugar to dissolve, but you're waiting for your food and you do all the packets on the table and keep putting it in there. Eventually the sugar will stop dissolving, right? And it'll just kind of pile up on the bottom. So there is a maximum amount that you could get to dissolve, and it is, again, temperature dependent. So one type of reaction, which is really important, which is a precipitation reaction. And when we talk about different types of reactions, which we are going to in the rest of this chapter, which is really talk about types of reactions, there's really two big classifications of reactions. There are double displacement reactions. And in a double displacement reaction, we have AB plus CD. And this is two ionic compounds. So that is how you could recognize it as a double displacement reaction. You got two positive, negative guys together. Whenever two ionic compounds get together, they pretty much will switch partners. So the two positive guys will switch partners. And on the other side, you will make two new ionic compounds. And depending on what happens here, one of the outcomes on the right-hand side could be that one of these guys makes a solid. And that is what is sometimes referred to as a precipitation reaction. And a solid is sometimes referred to as a precipitate, PPT. The other thing that could happen when you do this double displacement is one of these guys might actually make our friend water. And this commonly happens in what is referred to as acid and base reactions, or acid-base neutralization reactions. So the big classification of reactions is double displacement reactions. Underneath there, as we will talk about, is a more specific classification of the same type of reaction, where if you make a solid, it's sometimes referred to as a precipitation reaction. And if you make water, probably an acid-base reaction. All the other reactions fall under really another umbrella of reactions, which are referred to as redox reactions. And redox reactions stand for oxidation and reduction reactions. And in these reactions, you have basically, as we will talk about, a transfer of electrons. And between these two big categories of reactions, there's more specific ways to classify a reaction. And for example, in a redox situation, that's like where you find your synthesis and combination reaction, your decomposition reaction, your single replacement reaction, your combustion reaction. So as we go through the rest of this chapter, we're going to really talk about all these different types of reactions. And again, they basically fall under these two umbrellas. And the reason for that is when we talk about a chemical reaction taking place, there's really three reasons why it actually does take place. First reason is a solid is formed, taken care of by our double displacement reaction there, or precipitation reaction. Second reason a reaction takes place is water is formed, taken care of by our acid-base reactions under a double displacement. And the third reason why a reaction takes place is there's some type of electron transfer, which is pretty much all redox reactions. So all reactions, all different types of reactions that you come across pretty much boil down to one of those three things happening. Either a solid has been formed, water has been made, or electrons have been transferred. So that's pretty much the three reasons why things take place. Any questions on that? And again, they fall under these two big sort of categories, either double displacement reactions or redox reactions, which we will talk about each of these obviously as we go through this chapter here. Any questions on that? All right, so we're going to start our conversation here today, or the rest of today, with double displacement reactions. And we're going to talk about really precipitation reactions here to start with, and how we can kind of determine whether or not when we put these things together, should we expect a solid to form or not. So let's start with that. So a precipitate is when we do get a solid that forms from the result of mixing, for example, two solutions. So you could mix two solutions together, you could form a solid. This is your classic double displacement reaction. And if we look at it, that's a positive negative guy, that's a positive negative guy. And basically what happened is they switched partners. So my lead hooked up with the negative guy over here to make this guy. And then the other two also switch partners as well. My sodium hooked up with my nitrate to make my sodium nitrate. So these two guys got together on the other side. So let's talk a little bit about, say, this equation first, and something that we were talking about previously, which is if we had just the beginning parts here, which is our PbNO32, I think, and it was it sodium iodide, I think. Hope so. It was good. So let's say we had these two things and we wanted to figure out what goes on the other side, right? So earlier I was saying that you want to make sure that you get the correct formulas down, and you do want to make sure you get the correct formulas down, and you don't want to worry about the balancing. So when you have to predict, for example, what goes on the other side, you should think of each of these guys as what are the basic units or ions that are present here. So that is lead with a +2 charge. And that is nitrate, even though I have two of them, but it really is just NO3 minus. It's basically the basic unit of nitrate. Here I have sodium, which is a +1, and I have I, which is a -1. So when we predict on the other side of the equation, the formulas that come together, we should do it just like we do for naming, which is I am now going to put these two guys together regardless of my balancing aspect of it. So that's basically a +2 and a -1, which means that is how we get to this formula here. I need 2 of those I's. And when we put together our sodium and our nitrate, that is basically a +1 and a -1, which means I just need 1 of each of those, which is how I get to this formula here. That is also how I do not end up with like Na2, NO32, or any of those extra 2s. Now that I have all the correct formulas down, now I should do the balancing. And here I do have a polyatomic ion. So I can put my 2 there, put my 2 there. And I think I'm out of 2s at that point. And now I have a balance here. So this is what I was talking about earlier. Sometimes people will look and go, oh, wait, there's an extra 2 there next to the nitrate. I better put it into my formula on the other side. And you'll get the wrong formula and it won't balance. So always do it in that order. Correct basic ions, put them together correctly, and then go back and change the coefficient so that you get the right coefficient and the right formula. Any questions on that there? So this equation here, which is balanced, is what is known as the molecular equation. The molecular equation, we write everything in their proper formulas, everything balanced. But really, these guys are all going for a swim, right? So they all went to the pool that day. And they're all going to go for a swim. And because when I look at lead-2 nitrate, that is an ionic compound, which means it's a strong, weak electrolyte. It is a strong electrolyte, which means really when it is in solution, it is no longer together. There's some lead-2 flying around. There's some nitrate flying around, right? There's actually 2 nitrates flying around. So we could write another equation that describes what is happening actually in the solution. And that would be that there is a lead ion. And there are 2 of those nitrate ions floating around in the solution as pictured over there in my picture. Now, how about my sodium iodide? That is a strong electrolyte as well. It's aqueous, which means when it goes for a swim with those guys, there will be another sodium ion and a couple of them, right? Because there's a 2 in front, and there'll be a couple of the negatively charged ions floating around in the solution. And that means that this guy will actually break apart into 2 sodium ions and 2 iodide ions in this case. First off, any questions on that? Now, when we get to the other side, we do have a solid that's going to form. So what happens here is this lead that's floating around likes the iodides. So they'll all come together, and we'll go with green, but it is yellow, as you can see there in that picture. And they basically will find themselves attracted to each other and make a solid. And if something's a solid, when those 2 ions come together, are they still floating around freely? They're not. They basically just join together. So in this type of equation, because this is a solid, we would actually still keep it together. And typically anything that's a solid, anything that is a liquid, anything that's a gas for the most part, and anything that's a weak electrolyte will stay together. So when you're doing this type of equation that we're writing right now, any of those things, solid, liquid, weak electrolyte, you should keep it together. Now that leaves us one last thing here where I'm running out of room, but we got this guy here, which is our sodium and our nitrate. As you can see from my picture, they are still floating around, right? Freely in my picture. So they are going to break apart. So I'm going to write it underneath as I ran out of room. So 2 sodium ions plus 2 of the nitrate ions. And again, you normally just write to the right there, but I ran out a little bit of room there at the end. This equation that I just wrote is an equation that basically describes what's really happening in that beaker, that test tube, when you throw all those things together. You got these guys swimming around, you got some guys coming together to make a solid. This is what is sometimes referred to as the total ionic equation, or sometimes referred to as the complete ionic equation. And it is an equation that describes basically what is happening in that beaker, or whatever it may be, when these guys all come together. It is a ionic equation, which means the ions should have charges, which people somehow don't always want to write. Yeah. So again, if you write a formula for an ion by itself, it needs to have the charges included. So you got to have those guys in there. Any question up to that point? Now, when we look at the complete ionic equation or the total ionic equation, we should always be able to look on the left-hand side of the arrow and the right-hand side of the arrow, and we should find some ions that look exactly the same. So what ions look exactly the same? We have 2 of the nitrates that match 2 of the nitrates on this side. We also have 2 of the sodiums that match 2 of the sodiums on this side, right? So those guys are exactly the same. By the way, they're actually the exact same number on both sides, which is a good hint that if you don't have the same number on both sides, you probably screwed up balancing somewhere. These guys are what are referred to as spectator ions. So if you are a spectator, you're doing what? You're just watching. Yeah. So these are ions that, as you can see in my picture on the left there, they're in the solution, they're floating around, they're still having a good day, but they're really not making anything, right? They're not making a solid, they're not making the actual product that's being made in this case. So when we have spectator ions, because they're the same on opposite sides of the arrow, you think of the arrow like an equal sign. They cancel each other out. So basically we just draw a line through our spectator ions. And at this point, what we are left with is a third type of equation, which is really describing what is happening in this reaction. So in this case, that's the lead 2, finds the couple of iodides that are floating around in my solution to make my PbI2 solid. And this is what is referred to as the net ionic equation. And the net ionic equation basically cuts down to the heart of the matter and tells you when you mix these 2 solutions together, basically the lead from the lead 2 nitrate finds the iodide from the sodium iodide, and those 2 guys come together to make this precipitate. We made a precipitate here, which again is one of the reasons why a reaction actually takes place. So this is the reason why this reaction takes place, is this formation of this solid. Any questions on that there? So these are 3 important equations. Molecular equation, you write everything like normal, proper formulas like we did with naming. Total ionic equation, you break apart anything that is a strong electrolyte, anything that's again a weak electrolyte stays together, anything that is a solid or liquid will stay together, and you find your spectator ions and you cancel them out, and what you're left with is the net ionic equation, which basically describes exactly what is taking place in this reaction. Any questions on any of those 3 things there? Okay. So how do we know if we are going to get a solid or not a solid? We could use what I refer to as solubility rules to help us decide. And solubility rules, there are different ones. So what we're looking at in this particular table here are compounds that are typically soluble in water. And let us make sure we understand sort of what it means in terms of our symbols. If something is soluble, that means that it mixes, everything dissolves in each other. Those are guys that get the aqueous symbol next to it. So if you find something based on the table that is soluble, you get the aqueous symbol. And if something is insoluble, that means that they do not mix. You expect a solid to form. And those are the guys that get the S symbol or solid symbol next to them. So let's take a look at these rules. So these are guys that are typically going to be soluble in water, which means everybody on the left-hand side typically will be an aqueous, and they will get the aqueous symbol next to them. So basically that is group 1, lithium, sodium, potassium. That's also ammonium. They are pretty much soluble in everything. So as soon as you see a chemical formula that contains anybody from group 1 or has ammonium in it, you could pretty safely just roll over there and put an aqueous next to it. You know it will be a strong electrolyte. It's going to break apart. There are no exceptions, which is the right-hand column here. So the right-hand column, there's no exceptions. So whenever you have those guys involved, always going to be soluble. Nitrate and acetate, which is those two guys, also going to be soluble in everything. There are no exceptions, once again, here on the right-hand side. That means, again, that if you see a formula that contains nitrate or acetate in it, it's a no-brainer. Just put aqueous next to it. It should be a solution, basically. You will not get a solid that's going to form. Now, when we have chloride, bromide, or iodide, those guys are typically soluble, but there happens to be some exceptions over here. And the exceptions are silver, that is mercury 1. Remember, the guy with all the 2s is 1. And lead 2. So what that means is if you have chloride, bromide, or iodide with everybody except those 3, it should be aqueous. But if you have one of those guys, chloride, bromide, or iodide with either silver, mercury, or lead, it becomes the opposite of aqueous, which means it becomes insoluble and will be a solid at that point. Yeah. Any questions on that there? Our sulfate is typically soluble in everybody, but there are some exceptions: silver, calcium, strontium, barium, and lead. So once again, if you have sulfate with anybody except those guys, it will be soluble. But if you have any of those guys there with sulfate, then it will become the opposite and will become insoluble, and they will make a solid. Any questions on that there? Now, let's take a look at some more solubility rules. The next table is ones where they are typically insoluble. So these are some things that are typically insoluble. So over here, these are guys that are typically insoluble, which means they are typically going to be solids. Anything with hydroxide will be a solid, except basically our rule from the previous slide, that is group 1, and ammonium, which, as we saw, is soluble in anybody. So if you have sodium hydroxide, that is going to be soluble and will be aqueous if you have any of those guys there. Also, if you have calcium, strontium, barium, some people consider that to be slightly soluble. Sometimes you'll see SS for slightly soluble. Most of the time, slightly soluble leans more towards being insoluble. So most people think of it as being insoluble if something is slightly soluble. So usually insoluble, sort of how you would treat those guys. Sulfides are typically solids in everything, except for, once again here, group 1 and ammonium are calcium, strontium, barium. That would then make these guys aqueous if you had sulfide with any of those guys. Carbonate and phosphate are typically solid, except for basically group 1 and ammonium. So that group 1 from the previous slide kind of falls over. It still works here for these guys. So when we look at the one that we just did here, I think, which was this PbNO3 plus NaI goes to PbI2 plus our NaNO3. So if we were going to use our solubility rules to see how they got all of our states, first off, I look at this formula. You may not be able to find both things in it, but if you could find one that's helpful, in this case, I see nitrate, right? And nitrate is right here. It is soluble in everything. There are no exceptions. So as soon as I see that nitrate, I know this is going to be soluble and we'll get the aqueous symbol next to it. Right here, I hit sodium right off the bat, which is pretty much right there. That's group 1, which is soluble in everything. There's no exception. That's as far as I really need to go, right? And that would get the aqueous symbol. In this case, you could do iodide, and iodide is also soluble in everything except for silver, lead, and mercury. And in the case on the left, that is not silver, lead, or mercury, so it's still going to be soluble. So you could use both of them to figure it out as well. When we go to the other side, we may not see lead on the left, but once again, we do see I, which again is soluble in everything except for silver, lead, and mercury. In this case, that is lead. So instead of being soluble, it's going to be the opposite. And that is how we know this is going to be our guy that makes the solid in this case, which would be based on the solubility rules. When I get to the very last guy, that is sodium, soluble in everything. If I'm not convinced, I could go to nitrate, which is also soluble in everything. And that is how I know that guy would be aqueous in that case. Question on that there. So if I had so if I took a little silver nitrate and I react it with potassium chloride, why don't you write what you would get as a product and then also decide using the solubility rules what the solubility of everybody is. Okay, let's take a look. So I can recognize this as a double displacement reaction because that's a positive negative guy followed by another positive and negative guy. So I know it's going to be a double displacement reaction. The two positive guys are going to switch partners. So the silver will go and with the chloride, and silver is +1, chloride is -1, which gives us AgCl as the proper formula. Then the potassium will go and hook up with the nitrate. The potassium is +1 and nitrate is -1, which gives us KNO3. Any questions on those formulas? Now that I have the formulas, I want to make sure it's balanced. And in this particular case, it is balanced, this equation. We got 1 silver on each side. We got 1 nitrate on each side, 1 potassium, and 1 chloride on each side. So now we could go to our solubility rules here to decide what is going on. So first off here, we will look at our silver nitrate. And in this particular case, that nitrate is as far as I need to look. And that is going to be soluble in everything. So I know that this is going to be aqueous in a solution. When I come to the next one, I got potassium, which is group 1, will be soluble in everything. There's no exception. So that's really as far as I need to go in this case. When I come over here to silver, I may not find, but I do find chloride, which is over here. Chloride is soluble in everything except when it is hooked up with perhaps silver, which is the case here. So instead of being soluble, it's going to be the opposite, which means we will make a solid in this case, and that will be our precipitate. Lastly, potassium is soluble in everything. Nitrate is also soluble in everything, and that would be a aqueous solution. So this would be a precipitation reaction. That is the solid of silver chloride being formed here. Question on how to use solubility rules. Now, just to again show you here what we've been doing. That is not what I'm showing you. I'll try to show you again, maybe. All right, so we had silver nitrate plus our potassium chloride. making our silver chloride and our potassium nitrate. That is our molecular equation. Our total ionic equation in this case would be the silver nitrate is a strong electrolyte, so it will break apart into a silver ion and a nitrate ion. Our potassium will break apart into a potassium ion and a chloride ion. Our silver chloride here will stay together as it is a solid, and our potassium nitrate will also break apart as it is a strong electrolyte in this case. That means in this particular case, from our total ionic equation here, our spectator ion is nitrate on both sides, and it is potassium. These are our spectator ions. When we cancel them out, we get our net ionic equation about what is really happening in this case, which is the silver ion is going to get together with our chloride ion and basically make our solid, which is the reason why this reaction took place, of our silver chloride, which is our net ionic equation. Any questions on that there? All right, so we can use these solubility rules to predict what's going to make a solid, and obviously we use them for double displacement reactions, and more specifically really precipitation reactions. When we have going on here is just that solid being formed. Let's take a look at a couple of our solubility rules there. All right, so let's start with this one here. KOH, should it be soluble or insoluble here? KOH should be soluble, right? As soon as I see the potassium, it is group 1, so this should be soluble. Have the aqueous symbol next to it. How about silver bromide? It should be. Bromide is soluble in everything except for silver, lead, and mercury. So in this case, it's going to be the opposite, which is insoluble. And it should get a solid in this case. Calcium chloride. Chlorides are soluble in everything except for silver, lead, and mercury. And that is not the case here, right? So this should be soluble. Lead to nitrate, as we saw earlier, as soon as I see that nitrate, it is soluble in everything, which means it should be aqueous. And lastly here, our lead to sulfate is going to be insoluble, yes, which will make a solid. Again, if we look at sulfate, which is, where is sulfate? Right there. Soluble in everything except for lead is one of the exceptions, so it will be a solid in this case. Any questions on how to use solubility rules here? All right. So this is sort of what we've just been doing there. We want to write the molecular equation. Again, you want to write the total ionic equation. Strong electrolytes break apart completely. Again, weak electrolytes stay together. So for example, if we had something like, we'll do our HF plus our sodium hydroxide here. So this is a double displacement reaction. We have two ions here. And actually what happens is the H plus and OH minus come together to make water. And our sodium and our F here come together to make sodium fluoride in this particular case, which is also aqueous. So this is the molecular equation that's going on in this particular case. And to show you what happens when we get a weak electrolyte involved. So obviously we know our HF is a weak electrolyte. So when we go to write our total ionic equation, we're going to actually keep this guy together as it's a weak electrolyte. So it would be HF. This is a strong base, which means it will break apart into Na plus and OH minus. Now, water, which is a liquid, is one of those things that will stay together. Again, it's not going to make an ion, right? Water's covalently bonded, is sharing electrons. So we will keep it together. And this is an ionic compound, which will break apart into a sodium ion and a fluoride ion. This would be our total ionic equation. We'll call it a tie, yeah, total ionic equation. Our spectator ions in this case is what? It is just sodium in this case because we have that weak electrolyte involved. So it's only going to be the sodium that's going to actually cancel in this case. And what that will leave us for our net ionic equation is the HF will still be together like it is in the solution. We'll have a little bit of hydroxide happening. We'll have our H2O and we will have our F minus. So when you do have a weak electrolyte involved, got a little extra stuff hanging out, less spectator ions will cancel out. Any questions on that there? Again, weak electrolyte. So you do follow the same steps, except that you keep it together and it doesn't cancel out, obviously, that extra ion that normally would. Any questions on that one there? All right, let's try one last one here. Write the equation for the precipitation between potassium carbonate and nickel 2 chloride. Write the equation, the molecular equation, write the total ionic equation, and write the net ionic equation as well. All balanced. Figure out your spectator ions, figure out maybe what's a solid, if there is one. That we start out with the correct formulas. So we'll start with that. We know a precipitation reaction between potassium carbonate. So potassium is K plus, carbonate is 2 minus. So the correct formula here would be K2CO3. It told us it was aqueous, and we know it's aqueous because it has potassium in it, right? So potassium is soluble in everything, so definitely would be that. Also an aqueous solution of nickel 2 chloride. So nickel Roman numeral 2 means it has a +2 charge. Chloride is -1. So in this case, we need 2 of the chlorides. So that would be NiCl2. We also know it's aqueous because it told us, but more importantly, because it has chloride. And this is not one of the exceptions of silver, lead, or mercury. So we know it'll be aqueous. Any questions on that there? Now that we have this, we should also be able to recognize it clearly as a double displacement reaction, as it's a positive negative guy and a positive negative guy. What does that mean? It means that they're going to switch partners. So this guy is going to go to there, and we're going to go over here. I am not worried about the balancing aspect at this point. I want to get the right formulas down first. So when I take K plus and Cl minus, I get KCl. I do not get the dreaded K2Cl2. Yes, so that is not existing. Yes, so it is KCl. I know that this is going to be soluble as well because it has potassium, and that's soluble in everything. So you really do not need to look any further to decide that it is aqueous. I am then going to put it together with my nickel, which is +2. And my carbonate that's -2, so I just need one of those, each of them. And if you look at your solubility rules, you will find that this is indeed going to be a solid based off of carbonate there. And that would be our unbalanced equation. Any questions on how I got my product side? As you can see, I did not worry about the balancing aspect until I got down all the correct formulas. Now I should worry about the balancing part of it, and I can fix it by putting a 2 in front of the potassium here. And I think that fixes everything, I think, if I'm not mistaken at that point. I got 2 potassiums, I got 1 carbonate on each side, and I got a couple of Cl's on each side. Any questions on that? So this would represent our molecular equation. Now our total ionic equation, we're going to take this guy and break it apart into anything that's a strong electrolyte, basically. So this will break apart into a strong electrolyte. It's aqueous, it's an ionic compound. There are 2 potassiums, and we represent that by bringing the 2 to the front, and it should be K plus and the aqueous. That basically means we have 2 of these guys floating around, basically. There's also 1 carbonate, which is this guy. Again, they have charges because they are ions. When I come to my nickel 2 chloride, again, it's an aqueous solution, which means the nickel will break apart into nickel with a +2 charge. And that 2 means that I have 2 of these chlorides floating around. Again, not Cl2 on the bottom, but the 2 will come to the front, and that represents the 2 chloride ions that are floating around. Any questions on anything on the left-hand side there? Coming over here to my potassium chloride, that's also a strong electrolyte. And that 2 in front goes to everybody behind it. So when you break it apart, you get twice of those guys. So we will have 2 of the K pluses. And we will also have 2 of the Cl minuses, right? Lastly, here I have a solid. Should I break that apart or keep it together? Should keep it together, right? So NiCO3. This would be my total ionic equation. Any questions on that one? That again is describing pretty much what's happening where everybody's floating around in that solution as they go for a swim. It is from this equation here that we're going to find our spectator ions, and in this particular case, they should look exactly the same on both sides, and they should have the exact same amount of ions on both sides. So I have 2 potassiums that match the 2 potassiums on the other side, and I have 2 chlorides that match the 2 chlorides on this side. These would be our spectator ions. Once again, if you get to this part and you do not have the same numbers of spectator ions on each side, something went wrong with your balancing. Something is not balanced correctly. They should completely cancel out because they are spectator ions, so they should be exactly the same on both sides. Once we cancel out our spectator ions, we are left with what is truly happening in this equation, which is the nickel with a +2 charge from the nickel chloride is going to find the carbonate from the potassium carbonate, and they are going to join up to make the solid of NiCO3, and that will be our net ionic equation. Any questions on any of those parts there? Yeah. You do typically on the final equation, you mean? So kind of like what we do with naming and nomenclature, we always go kind of positive then negative. So typically in an equation, you'll kind of do that as well. Is it technically wrong if you went negative to positive? It's probably okay, technically speaking. But usually we'll kind of go positive then negative, kind of similar to what we do with naming. Other questions?